It, it always seems like this side of the room is more densely populated than that side, which is odd because you have to walk by that side to get. This is like all the cool kids sit in the back of the bus, right? You have to walk by the front of the bus to get to the back of the bus. This must be all the cool kids in the class. I was like sitting in the front of the bus because you could see what the driver saw, and you knew if you had to do this. So as we get started, who's got a cool bus driver story from high school? Who never rode the school bus in high school? Anybody? A few of you never rode the school bus. You won't have any cool bus driver stories, unless you did sports.
I take the normal bus.
Oh, you rode a regular bus?
Yeah.
My daughter just told me last week that she was talking about some of the teachers. She's a freshman in high school. She's talking about some of the teachers being real hard asses about getting to class on time. And they'll give you detention if you're a minute late. And the very same day, she's texting me in the middle of the day, like she's in class and texting me, could you pick me up after school? I was like, yeah, at 1:45 when school ends? No, a little bit later. And then she like stops texting. And I'm thinking, she got detention for being late for class. Now, it turns out she had to stop texting because the teacher was calling her out as an example to the class as being the only kid who was paying attention. Now, in the meantime, she's got her phone under the table and she's texting me. So I complimented her. She was just way better than the rest of the students at pretending to pay attention. And it wasn't detention. It was she had to stay late to copy out some problems for a class she was taking. But anyway, while everybody's getting in here, getting settled, cool bus driver story. We had a bus driver for sporting events. I guess he may have driven the regular bus to and from school, but I think he really only drove sports teams to events. I was on the track team. It doesn't look like it now, but I was a track star in high school. Except this was winter. This was probably cross-country skiing. Anyway, we called him Mr. Bus Driver. Seems like a thing that you'd call the bus driver. So Mr. Bus Driver was actually a state senator, and bus driving was like his day job because it was Vermont. They don't pay the state senate very much. But he was a senator and Mr. Bus Driver. And we were going up a hill on the way to a ski area probably. And who's ever driven in Vermont? Who's ever driven in the snow? Rear-wheel drive vehicle. What happens when you apply more throttle?
Nothing.
Oh, rear-wheel drive vehicle on the snow, more throttle, the back of the car becomes next to you. So picture this with a bus, school bus. So there's some guy coming down the hill, and Mr. Bus Driver says, watch this. And he steps on the gas. Of course, the back of the bus comes around because that's what happens when you apply more throttle. You kick the back end free. And the car coming down the hill, into the snowbank. We kept on going. My favorite school bus story. I also, different school bus. I was once on a school bus that almost went off a cliff. That time, bus driver, icy road bus driver saved us. Drove into the snowbank to keep from going off the cliff. So that was cool. Anyways, I want to apologize in advance for today's lecture. I have a PhD in the stuff we're going to talk about today. Like we could talk about the actual stuff I did my dissertation research on, and if that happened, I mean it's not on the agenda, but we could. I've tangented before, right? Flown off on a tangent. We could end up there, and if we end up there, I might just keep talking, and the day may never end. But I'm going to try to stay focused. I'm going to use some slides today to try to stay on track. But I just want to apologize that if I seem like I care way too much about this stuff, it's because I do. All right, so let me get the slides bigger. This computer, I can make the slides bigger. Make me smaller, slides bigger. There we go. Now let's see if I can use the slides. Yeah, I don't want to play the video again. There we go. All right. So I think when we talked about quality, we talked about measurement, right? Way back week 1 or 2 of the class, we talked about quality in manufacturing. What's quality in manufacturing again? What is it? Quality in manufacturing? Yeah. Yeah, so give the customer what they need when they need it. So quality in manufacturing is giving the customers what they need when they need it. And did we say how we know when we have quality? Say again? So we know that we've had quality in the past because they pay us. How do we pre-anticipate that they're going to pay us? There's 2 things we could do. We could never make bad parts. So we could have our process so dialed in that it's impossible to make a bad part. Or we could do some quality inspection before we ship the parts to the customer, right? And typically in manufacturing, we try to do the first, right? We try to make it so it's impossible for us to make a bad part. But then we also do some quality inspection to make sure we don't ship bad parts to people. What are the kind of things that we inspect? Yeah.
Dimensions.
So we inspect dimensions. So physical dimensions, I'm going to call that geometry. Okay? So geometry. And so this means like the thing is 5 inches, supposed to be 5 inches long. Is it 5 inches long? 3 inches wide. Is it 3 inches wide? Yeah. The finish. One F or 2? Oh, sorry, not F, N. I meant to say N.
I think the 2 N's would be like
Right. So this is the people. Right. But this is the thing he meant. Unless it happens, unless you were talking about the people.
I think we always need to check on the finish.
Hey, they're NATO members now.
Oh, they are.
They're like our buddies.
Okay.
Don't pick on the Finns. I lived in Sweden for a while, and people make jokes about neighboring countries. And I know some really good Finnish like jokes about Finns, but none of them are appropriate to say in front of the class. But the Finns, all right. So the Finnish, and so when you say finish, what do you mean? No, wait, never mind. You be quiet. When he says finish, what does he mean? Yes.
like the surface of the part.
So like how rough it is if you looked at it, or if you like dragged something across it. Is that what you mean?
Yeah.
Yeah.
So like maybe how much.
So we may call that surface finish. So we might call that surface finish. Often we call it roughness. That's sort of common use. We'll say things like finish, surface finish, and roughness, and use them interchangeably, especially in common speech. What else could finish mean, though? Yeah. So it could also mean like a coating. So a coating, the paint. Now, what makes? Yeah. So there could be, so it could actually be microgeometry, right? So those burrs that he's talking about. So who's picked up a machined part? Most of us have, right? Who's run their thumb or their finger across the edge of the machined part? We all have, right? Because we all are a little bit ADHD, and we all fidget with things, and sharp edges are cool to fidget with, right? Right? We could do this, like if this had, oh, there's kind of a sharp edge. Yeah, I could do that for hours. I wouldn't even know I was doing it after a moment, right? I would just keep rubbing my thumb. Well, actually, on the piece of chalk, it would probably go away. It would become smooth. But that's just a different tactile sensation, right? And so the thing you feel when you rub your finger across the edge of a machined part is a burr. We made the rolly stick things first week of lab, second week of lab. When it cut off in the lathe, there was a little nib that stuck out the end, right? So the part looked like this. And then one end, there was this little thing that stuck out. Why did that little thing stick out on the end? Which end was it? It was the end that got cut off, right? So it was the end that was closest to the chuck. But the other side, the part that got cut off from, was smooth. It didn't have a little thing sticking out. Why does the little thing stick out on the end of the part? You guys have enough knowledge to answer this question. Right, because all that cutting has to have a cutting force, right? Eventually, the cutting force exceeds the strength of the material that's left, and it just breaks off. So it fractures right there, right? Now, why did I bring that up? Anybody know? What were we talking about just before that? Finish. Burrs. Oh, we were talking about burrs. Right, so on your other machined parts, let's say you made a part where the side of it is like this, and maybe you had a big face mill go across it like that. We made a part like that, right? The base, we used a face mill, we went across the top of the part. We put a chamfer on that edge, but even with the chamfer, you could feel a little bit of sharpness right on that edge. That's because right at the edge of the part, it doesn't have the strength to stand up when the cutting tool hits it. So instead it folds over. So the edge of the part folds over. Every machining operation is going to have a burr. You can keep refining it to make the burr smaller and smaller, but that's what he means when he says the burr on the part. And I really think that that's, people tend to group them in with surface finish, but I really think it's microgeometry. It's small geometry, not surface finish. But sure, we can use surface measurement equipment to measure those burrs. So besides geometry, surface finish, which maybe coatings, we can measure, right? We can measure magnetic properties, and we can measure the mass of the thing, and we can measure the color of the thing. I once made a colorometer or a colorimeter. Really, really black box. No light can get inside, except for the light you put inside. Camera on the top, and then full spectrum lights inside the black box. And you put your sample in. You light it with the full spectrum lights, take an image with the camera, and before that, you calibrate it with something you know the color of. And then you can compare the colors. Colorometer or a colorimeter. Anyway, so you can measure all those different things. So today, you guys know how to measure length, right? All this is length. That's the thing we typically measure is length. And we can measure it with different precision. So we can measure it, well, two of you stand up. So how tall are you?
Like 5'6".
So you are 2 fingers taller than he is.
Congratulations.
Right? So we can measure things by looking at them. We can measure with a tape measure. Who's used a tape measure? We all have, right? We measure, I mean, some of us have used the one where you wrap it around your belly. I never liked the one that says, never liked that one. You can measure with we use calipers in the lab, right? Used a go, no go gauge in the lab. You should have at least. And so the go, no go gauge is something that we know the diameter of. And does one of them fit in the cylinder? Does the other one not fit in the cylinder? Right. So there's a bunch of different ways that we can measure geometry, but it's pretty much all measuring length. And it depends how much precision do we need. How do we measure surface finish? Yes.
There's the machine that you were telling us about in the lab with Walter Tower, the thing, it's like a rectangle, and all across the surface.
Wow, you paid attention. You paid attention to that class. That was like 3 weeks ago in the morning, 8 o'clock in the morning. We talked about that.
Yep.
Wow, I can hardly remember it. So one way we do it. So one way, who's everybody still knows what a record player is, right? Phonograph. Yeah. So how does it work? Yeah.
There's a little groove inside of there, and as the needle moves through, it vibrates, and then that is like.
Well, if it's a groove, it just wouldn't it just follow the groove around?
Well, no, it's like when they're making it, they put like sound waves into it.
So all right, he's got it. So there's like a needle. Often they use the diamond tips on the needles. So it's very small. We're talking maybe the radius at the bottom here of the needle is 5 micrometers. So how big is a micrometer? It's 1,000th of a millimeter, right? So small. So you've got that needle, and in that groove, so there's this spiral that goes in on the record. At the bottom of the groove, there's a bunch of ups and downs. As it goes across there, it vibrates. Vibration makes sound. All sound is vibration, right? It makes sound. They have amplifiers. They put that sound out there. So you could use that same technology, and instead of listening to the sound, you could record the signal that comes off. And so the second, maybe third, the third most basic way we measure surfaces is by dragging basically record player needles across them. Although I did, who's ever heard of an atomic force microscope? Few people. Same exact principle, except the tip on the needle is nanometers instead of micrometers. And it's made out of like silicon, and it's got a little sharp point on there. So as we do this, two things happen. As we drag this needle, and it doesn't matter which size needle it is, the needle could be this piece of chalk. And I could use this piece of chalk to measure the surface of the table. It has the same impact. Now, what happened to the table, if you could imagine, when I used the piece of chalk on it? Chalk left the piece of chalk, and probably table particles left the table and joined the chalk. That's harder to tell, but it probably happened. So you can imagine if you're measuring surfaces like this, when you're done, you're going to have changed the surface, and you're going to have changed the tool you use to measure it. Is that okay? It's unavoidable, right? There's some famous scientist guy said you can't observe anything without changing it. I forget who it was. One of those famous scientist people, though. even looking at stuff can change it. So they say. All right, but anyway, what happens though, if you take a surface and you do this a bunch of times, maybe not exactly the same space, you can move around on that surface, you get this signal off there. If you sample that signal, what you'll end up seeing, this is one of the points of my PhD, is you can never actually measure a surface. You can only measure the interaction of your sensor with the surface. What we do is we sample it digitally, right? So we end up with a bunch of points. We could connect the dots. But when we connect the dots like I just did, we have guessed about all the points in between the ones we measured. We only know things about the ones where we sampled it. And we know that while we were sampling it, we were moving the part as well as damaging the needle. How could we do it better? Yes.
Find some way of measuring the surface that doesn't involve actually touching it mechanically.
Perfect. That was what we did next. Actually, what we did before this, you've all done an infinite number of times. Well, I guess it's a finite number of times, but we haven't been able to count it. We've done this. We've touched the surface, right? So actually take your thumbnail or take your thumb. Everybody's got a thumb, right? Nobody's got like their thumb cut off. It could be awkward for me to tell you to use your thumb and then have you not have one. But take your thumb, take the surface in front of you on the table. There's two surfaces on the table in front of you, right? There's a wood surface and there's some kind of laminate surface or plastic surface. Can you immediately tell the difference between the two surfaces? You have now characterized the surfaces. You have measured the surface texture of the surface. You haven't calibrated it because you don't have a number to put next to it. But you know which one is smoother, right? Which one is smoother? For me, it was the wood surface was smoother. Is that the same for you? It's because the wood surface has a coating on it. Some kind of plasticky coating on top of the wood surface, right? All right, so that's the first way we measured surfaces. We touched them, tactile. Second way we measured surfaces, we actually wanted to be able to quantify that somehow. We looked at them with a microscope. But you say microscope, that gives you a sort of a two-dimensional flat image, right? When you look at something through a microscope. Who's ever used a microscope and had stuff be out of focus? Who's turned the little knob to move the lens up and down to put it in focus or out of focus? So what this guy did is he looked through his microscope and he had the lens set up so that there was a very narrow depth of focus. So only a narrow band would be in focus. And he went down until everything was out of focus. Then came back up until he could see stuff. And then he counted how many spots where he could see stuff. And he came up a little bit more so he could see different stuff. And he counted how much stuff he could measure there. And so he built basically a set of layers of how much stuff was at that height in the field of view of his microscope. And that was the standard for measuring surfaces until somebody figured out you could use a record player needle to do it. And in the 1930s or so, they got really good at doing it with a record player needle because in the 1930s, they'd figured out RC circuits. And so they could actually get numbers out of the signal. And they could do it with electronics. And so you could just have it output a value and tell you something. Because picture's worth 1,000 words, right? And we're engineers. We like pictures. But man, numbers are cool too. Because numbers are easier to compare with each other. It's hard to compare two pictures. Easy to compare two numbers. And so they did that. So you want to go now to the next level of doing it without touching the surface. That's cool. How do we do that? Besides the microscope thing, which, by the way, there's a super high-tech, $200,000 instrument that still does it the same way the guy did with the focus variation. But you can pay a lot of money to do that now. How else would you do it besides that without touching it? You could take a picture, and actually that's how we do focus variation now when we measure surfaces, is we get that very narrow depth of field. One of the ways you do it is you shine the light through a pinhole, and so it'll narrow the depth of field, and then you move the pinhole all over the surface. So you take a bunch of images, and then you use image processing to reconstruct where the surface was there. But to just take one picture, it's kind of hard to get three-dimensional information. You can see the spatial information, but it's hard to get three-dimensional information. You can do a stereo picture. And so that's something that people do. They'll take a picture from two different angles. They'll see how the different things show up as pixel shifts, and they can get some information about the different heights of the thing. Yes?
There's atomic force microscopy.
So atomic force microscopy is exactly the same as the record player needle, just smaller scale.
Oh, okay.
Yep. Oh, they do use a laser interferometer to see how much the needle has moved up and down inside the atomic force microscopes.
Oh, okay.
But you can use the laser directly on the surface too. There's different ways of using the laser on the surface, but basically you can shine a light down, have a light sensor over here. If it's a laser, then it's a really focused light, and you can see how much of the light scatters back to this orientation. And you can determine how far away it had to be for that much of the light to scatter back. And so you can triangulate the surface with a laser triangulation sensor. And this is maybe not the most popular non-contact way to do it, but it certainly is one of the most prolific ways of doing that with non-contact, where they use that laser profilometer. We call it a laser profilometer. The one with the record player needle, we just call it a profilometer, laser profilometer. So, does the laser touch the surface? It does. Several years ago, I was doing a study where I think I talked about the chocolate bars, right? Did I already talk about chocolate bars in this class? With your group? Yeah. So, who's ever had a chocolate bar where the surface looked white? So chocolate itself is actually an emulsion. It's just a mixture of stuff that's put together. And hot-cold cycles will make the sugars and the fats come to the surface on the chocolate, and that's the white stuff you see. So it's all the same ingredients. They're just not arranged in a pretty manner anymore. So it changes the surface texture. And so we could actually say how much, they call it blooming, how much blooming had happened on the chocolate. And we actually built a heat treating system to cause the chocolate to bloom faster. So we could see, because it's hot-cold cycles that do that. And then we were measuring it, and we knew the record player needle would scratch the chocolate. So it was like, we'll use the laser. Chocolate melts at 85 degrees Fahrenheit. Our laser could heat the chocolate to 85 degrees Fahrenheit at the point if we moved too slow and if we had the power setting up too high. But chocolate is dark in color. The laser metrology likes to use high power settings with dark materials because it needs to have enough light scatter back. It was a thing. So even non-contact measurement sometimes contacts the surface. All right, so what do we do with all the data once we got it? Let's go to a new slide. Oh, yeah, this was the end of the last presentation, right? We talked about standard deviation and statistics, and I said, bring data and you can do math, right? Did I show this one last time? This is my fun slide. All right. We should talk about a little bit about accuracy and precision. So accuracy is closeness to the true value. Precision is closeness of the measurements to each other. How do you know what the true value is? How do you determine if your machine is accurate, if your measurement is accurate? Whether it's a ruler, whether, or the laser interferometer or the atomic force microscope, how do you know if it's, precision's easy, right? I mean, here we just measure 4 times and see how close to each other the 4 measurement values are, right? So how do you know if it's accurate? Yes?
You have to measure something that you already know the measurement of.
Right. You have to measure something you already know what it is, and you calibrate your system with this known value. So how do you know? It's easy. Somebody just decides. And then if you decide about one standard and then compare everything to that standard, you can, is it truly accurate? The just deciding was kind of arbitrary at the beginning, right? But it's at least accurate to some comparative value. We talked about the inch, right? How long's an inch? 24.5 millimeters, right? So there used to be, we used to have a standard. It was a piece of gold, and there was 2 marks on it that were a foot apart from each other. And you could compare everything to how far apart those 2 marks were. And we stopped maintaining that standard of the foot because Congress legislated that the inch was 25.4 millimeters. And when we did that, there was, in Paris, there was a meter long piece of gold. I guess their gold was more expensive than ours because it was longer, right? And so then we had a standard. There was one. It only works if there's one, right? And then you compare, you could make your own and compare it. The reason gold is because it's really stable material. Doesn't degrade very easily with contact with air and stuff like that. What's the meter based on now? They don't maintain the golden meter anymore either. I'm sure it's in a museum somewhere.
I'm pretty sure it's based off of the speed of light in a vacuum now.
It's based off of how far light travels in a vacuum over a certain period of time. So we trace all of our length measurements back to the speed of light now. So we start going faster, and all bets are off. But anyway, so accuracy, you compare it to a known standard. Somebody makes up the standard, and then we all, and it's a big industry to make the standards to sell them to people, because everybody's got to prove their thing is accurate. You don't necessarily need accuracy if you're controlling the process in-house. You just need precision. You need to know the difference in size between 2 items more than you need to know exactly what the size is. But if you're a manufacturer that's making stuff for other people that said how long it needs to be, you need precision and accuracy in order to be able to do it. So we can measure with calipers, micrometers, indicators, all that stuff. Coordinate measuring machines are just computers. It's basically like a CNC machine tool, except instead of a cutting tool on the end, it's got a little ruby tip on the end, and it's got a little switch in it that knows if the ruby tip touched something. And so you go around and touch stuff. It's only as good as its last calibration. Just like when we measure the tools and the workpiece in the CNC machine tools, it's only as good as its last calibration. We can measure all these things. All right, this is what we're talking about today, though. Surfaces. Surfaces cover everything. In fact, the objective of every manufacturing process is to put particular surfaces in particular locations. That's the objective of every manufacturing process. So a surface, and it's really the boundary between 2 things. So the surface of the ocean is the boundary between the air and the water, right? The surface of the table is the boundary between my fingertips and the inside of the table. And so surfaces are just that layer on the boundary. So we've got surface creation. We can study how we make surfaces, and we can study how surfaces behave. What kind of physical things does the surface itself impact? So does it impact mass? Typically not. I mean, I suppose if you get a complex enough surface, it may have more mass than a less complex surface. But typically, the surface doesn't impact the mass of the part. What kind of physical properties would the surface impact? Friction, right? Two surfaces sliding on each other. You can imagine that two smooth surfaces are going to slide easier than two rough surfaces. Okay, what else? Signal propagation on wires. Depending on the surface texture on the outside of the wire, the signal will travel slightly different speeds. Actually, if you get enough roughness on there, it acts as like an antenna and it travels faster through air than it does through the wire. So signal propagation, kind of cool stuff. Heat transfer. Turbulence, so airflow. So as air is flowing over a surface, if you change the surface texture, air is going to flow different. Adhesion. You're going to put a coating on a surface. I spent a lot of time looking at surfaces that needed coatings. We looked at the you don't have to raise your hand if you don't know, but who drives a vehicle with aluminum engine block with spray coated cylinder liners? So if you've got an aluminum engine block, there's a good, well, it's not aluminum cylinder walls. It's either a cast iron sleeve inside the cylinders, or it's a sprayed on coating inside the cylinders. So when GM was doing this, they were building race cars, like the Corvettes for the GT circuit or whatever, where they do the racing, the Grand Prix stuff. And they were spraying on their coatings, and we got the project to determine before they sprayed the coating whether or not the coating was going to stick. Because it turns out it's a big deal if the bits of coating come off in the middle of the race. Well, I mean, it's only a big deal for that one car and whoever runs into them when the engine stops. So adhesion of stuff. Who's read on a spray can? Right, you're all old enough to buy spray cans of paint now, right? 18 is the age. Most of you are probably old enough to buy cans of paint. It says right on the can of paint to roughen the surface. Doesn't say how much. Nope. I know a guy that got a PhD trying to figure out how much. All right, but anyway, so those are the kind of behaviors. Surface creation. Wrong keyboard. Oh yeah, no matter how hard we try, the geometry is chaotic. So surface metrology is the measurement of surface. We look at topography, so that's more geometric stuff. Roughness, waviness, and lay. So what we do is we take out. So a surface could easily. That one's already got stuff on it. There we go. So there's two scales that we can clearly see in this drawing here. We've got some fine scale roughness, and then we've got a long wavelength waviness. That's the difference between roughness and waviness. The person measuring it gets to decide what frequency they decide is fine scale and large scale. So it's just a way to separate these two things, which we often see when you in the picture on the screen, you see you can kind of see that there's roughness and waviness in that picture, right? It's not as regular as my attempted sine wave with squigglies on it, but you can kind of see that. What is this surface? Oh, that is carpet. We were looking at air quality, and so more texture on the carpet would mean that it could trap more particles, and then those particles could potentially be there when you step on it to get released into the air. So, or it could trap more particles and hold them if it has the ability to hold on to the particles, if it can adhere them, that particular surface. Anyway, in our CNC machining, pretty much all the processes do something like this turning process here. And so you remember we drew out our part here. So if it's rotating this way, I put the tool up here, right? The tool's feeding in that direction. So you remember this diagram. So on this surface, we actually have, and the radius here is the radius of the tip of the tool. And the distance between them is the feed in inches per revolution, or distance per revolution. If we're using metric units, it's millimeters per revolution, right? So that distance between them. So with just, I want to say 7th grade, but I don't think it is 7th grade, but where you do chord lengths and stuff like that. There was a math class in high school. We had to figure all this stuff out, right? I vaguely remember I probably was sneaking out. I didn't spend a lot of time in math class in high school. It was kind of boring, and it was easy to sneak out of the classroom, go to the cafeteria. I had math class in the morning. I remember very specifically 9th grade at least. It was geometry. I forget the teacher's name. It was a really old guy. And I sat in the back of the room. I would be like, Mr. So-and-so, could I go to the bathroom? He'd say, yeah. I would leave, go to the cafeteria, get a cup of coffee and a fried dough with cinnamon, powdered sugar, eat my fried dough, drink my cup of coffee. Near the end of the class, I remember one time not wanting to be seen coming back so late, crawling, and then just get back in my seat. I didn't spend a lot of time in math class because math was easy. It was boring to spend a lot of time in math class. But there was a class where we figured this stuff out. I don't remember any of that stuff anymore, probably because I wasn't in class that day. But I do know that I can look it up in a reference manual. And so you'll find if you solve this, the top one's a quadratic equation, right? Because it's got the squares. Is it truly anyway, if you solve that, there's more than one possible solution, but this is the best one. So this RT, that's the height from here to here. And so that's a commonly used measure of roughness. And you can figure out what it is mathematically. If you want to have a smoother surface, what should you do? So this is a turning operation. If you want a smoother surface, what do you do? Yes. Slow down the feed and or
Increase the radius of the tool.
Bigger tool nose radius, right? Either one of those will get you a smoother surface. So now when you see on your part drawing and it says the surface roughness you need, you have some idea of how to adjust your process parameters to get that surface roughness, right? Yeah, here's the proof of that. But when we measure surfaces, they're not perfect. And so we actually have this instrument downstairs in the lab. It's a surface profiler. This one, in fact, is a profilometer. It's like a Kleenex. Everyone in industry calls any surface profiler a profilometer because they were like the best marketing at the beginning. But this one is, in fact, a profilometer. It's a profilometer PRK from like 1980. They gave it to us because it was old and they changed their corporate colors. But at any rate, drags that record player needle across. You see how it goes kind of, so you got some waviness. It's probably 2 frequencies of waviness that I can see on this part. And there's some roughness. So if I had this one and then I had one that went downhill and I tried to figure out like what's the average up, down, they would be completely different, right? So the first thing we want to do is we want to level that relative to itself. And so we level it and we set the mean value equal to 0. when we're processing these kind of profiles. So you level it, set the mean value equal to 0, and now I can compare profiles from 2 different parts measured with 2 different machines, and I can compare the 2 of them because it's just showing the relative ups and downs of them. And then what we do, because we're engineers, we like numbers. Pictures are cool, but we like numbers. We calculate these parameters, and so I've got three parameters listed here. I talked about the RT. That's the maximum peak to the minimum valley on average throughout the profile. The RP is just the peak above the mean line. And then the RV would be just the valleys below the mean line. Now, the most common parameter that we see, I bet it's on the next slide, is the arithmetic average. It's the average distance of every point from the mean line. It doesn't care if they're above or below. It's the average. This is the most common in the U.S., in Europe, and in Japan. They tend to, instead of using average roughness or RA, they tend to use RQ, or the root mean square. It's just a different way of calculating the average, basically. So this RA, if I had a surface that looked like that, and another one that looked like that, they could both have the same. Make this green bigger. So if I had these 2 surfaces, they could easily both have the same RA value, but they would definitely perform differently in practice, right? So RA, it's the most commonly used parameter in industry, but it doesn't tell you very much about the surface. Why is it so common? Why would it be the most common if it doesn't really tell you that much about the surface?
I'm guessing it's easy to calculate.
It's very easy to measure and calculate. That's one reason. Yep.
It's probably easier to be able to just give one number instead of like 15 describing different like surface parameters.
Yeah, I actually know another guy that worked on his PhD trying to figure out which parameters correlated with each other mathematically. Right, because what if you specify it's got to be this RA, this RT, and this RV, but RA and RT and RV are all correlated with each other the way they're calculated. So you could possibly define a specification that's impossible to make. So that's why the guy was working on his PhD on that. I did say I geek out on this topic. The reason we use RA typically is because it's really cheap to measure. You can buy a tool that can measure RA very, a couple $1,000s as compared to a couple $100,000 to measure a more complicated thing. If you're going to control your process on the manufacturing floor, you'd like to have the cheaper tool if it gave you a good enough answer. And it works perfectly for controlling the process, as long as you don't change the process. As soon as you change the process, you're going to have to calibrate the system again. You're going to have to actually go deeper into the math to figure out, is RA still the thing? I'll end on a couple of stories. One was, who's ever used a film camera? Take a picture and print it out on film? Most of us have. So Kodak was a big manufacturer of film and paper for printing pictures on. And they would get these rolls, one roll. So they put the texture on the paper. The texture impacts how well the ink sticks on it and how it looks when you look at the thing. They have these giant rolls that come in on a train car that put the texture on the paper. And they, I don't know, $50,000, $100,000 for one roll. And so it comes in and they measure it with their service profiler and it meets the RA spec. They put it in the machine. Here's what a day of the machine not working. So that costs money. Put it in the machine, start making paper with it. Paper's no good. But it met the spec. So the vendor, the people that made it, they were good. It took us about 15 minutes in the lab to figure out which parameter they should have spec'd to get good parts. But what they knew was they knew RA. So if you remember anything about surface metrology, it's that RA is not always the right parameter, and think about the physics of the process before you just define it if you go to become a designer. One more quick story because we have 2 minutes left. Oh, no, we don't. Anyway, I'll talk really fast. This was aircraft manufacturer making wing spars for fighter planes. And so you don't want them to fatigue because wings on airplanes get loaded like this, right? And so and it happens really fast. So it's like this, but I can't move that fast. And so that repeated motion can cause, the wing to break off. I'm not going to do that with my arm, but because of fatigue. It's little valleys like this that cause fatigue cracks to start. Bumps like that don't cause fatigue cracks to start. The machining process they were using was making bumps. Their specification was to not have valleys. They were measuring with RA. They calculated it costs some number of millions of dollars a year because they had the wrong parameter specified. Millions of dollars a year because they had the wrong parameter specified. Of course, they didn't change anything because, hey, the wings were not falling off the airplanes. If it ain't broke, don't fix it. But at least they knew that they could change it and save money. Surface metrology, I hope I didn't get too tangenty. We didn't even talk about my topic. It was surface roughness, waviness, and lay. I was all about lay and chaos theory.